This is the second part in our lesson on vectors in a plane. In the first video, we talked about what a vector is and how it's a quantity that has direction and magnitude. And we represent these vectors by ordered pairs like 3, 2. And graphically, we can represent them as an arrow in the coordinate plane. So now we're going to take a look at what we call unit vectors and standard unit vectors and some other notations for describing vectors. Continuing on with our handout here, we're going to look at unit vectors. And what a unit vector is a vector that has length 1. And we found out earlier that when we multiply by a scalar, it just changes the length of a vector, it doesn't change the direction. So when we want a unit vector that's in the same direction of our original vector, then we can take our unit vector is just the vector itself, which is written in component form with 2 numbers, divided by the length of a vector. This absolute value of v means the length of the vector. Another way to write that is 1 over the length times the vector itself. So this is what we call a unit vector in the direction of v. For example, let's say we have our vector negative 4, 5. So here we have the vector negative 4, 5 sketched in the coordinate plane. And it's going off to the left. What we want to do is we want to find a unit vector that is shorter than this. So the first thing we need is we need to find the length of v. How long is this actual vector? And the length comes from the Pythagorean theorem. And so we're going to have, since we're going over 4 and up 5, we just need to use the Pythagorean theorem. It's going to be the square root of negative 4 squared plus 5 squared. So we're just going to take the 2 components and square them, add square roots. So that's just the Pythagorean theorem. So we have 16 and 25. And that comes out to be the square root of 41, actually. All right. So we got the length, square root of 41. Can't simplify it, so we'll leave it alone. Now, according to our formula up above, our unit vector should be 1 over the length, the square root of 41, times the component form of v, which is negative 4, 5. And as we saw in the first part of the lesson, when we multiply a vector, here's our vector, negative 4, 5, by a scalar, this fraction, which is just a simple single number, even though it has a radical, it's just a single number there. We basically distribute. We're going to multiply both components by that, and that gives us negative 4 over root 41 and 5 over root 41. And there's our unit vector. All right. Now the second part of the question is we want to verify that this unit vector actually has the length of 1. So let's go ahead and give that a try there. So what we're going to do is we're going to find the length of u. And we're going to do that again with the Pythagorean theorem. The square root of negative 4 over square root of 41. Now it's squared, and we're going to add 5 over root 41 squared. And that's going to give us the square root of 16 over 41 plus 25 over 41, which is root 41 over 41, which is just the square root of 1, which is 1. So we have length 1, and that's what we were looking for. Checks out. Fantastic. All right, so if we look at this as a decimal form, this vector that we just found, u, is really about 0.62 and about 0.78. Okay, so 0.62 and 0.78 will put us with this little vector. It's going to be hard to draw perfectly, but it's going to be a little vector right down here in the same direction as this one that we had right down here, and it's going to have a length of 1. So a little vector down there. Same direction as v, but it's a length of 1, and that's going to be useful in lots of applications. Now, to take this a little further, we have what we call standard unit vectors. We've got 2 special vectors. We have the vector 1, 0, and that's in the coordinate plane. That's just going right 1. And we have the vector 0, 1. That's going up 1. And since we saw that vector addition can just be made by adding components together, this becomes a useful way to write a standard unit, a vector in terms of these two standard unit vectors. So let's try that out. So we have a vector v that starts at a, which is at 2, 0, and goes to b, which is negative 1, 3. And we need to sketch the graph of the vector. We're going to write v in terms of I and j, and we're going to write it in component form. We might actually want to go component form first. So sketching this first from 2, 0 to negative 1, 3, we get this vector right here. And to find the component form, we're going to subtract the coordinates. And so let's call this v. V is going to give us, we're going to subtract the x coordinates, the terminal point, negative 1 minus 2, and the second coordinate, 0 minus 3 minus 0. And that's going to give us negative 3, 3. And as we can see, that vector is going left 3 and up 3. So what this means now is we can write this in terms of these vectors I and j. Okay. Now j is going up in 0, 1. So the idea is this. We're going up 3 units. So 0, 1 is going up 1 unit. And if we're going up 1, 2, 3. So if we have 3 of these j vectors going up, and we're actually going left 3 also. So we're going to go left 1, 2, and 3. So to write this, we can say that v is just made up of 3 negative I vectors, because we're going left 3. 1, 2, 3. So that's 3 of these guys in the opposite direction. And we have 3 positive j vectors. So this is what we call, written in terms of I and j, standard unit vectors. And this one over here is our component form. Now all this means, just to kind of make it hopefully a little more clear, we said up above we defined I as 1, 0 and j as 0, 1. So I is 1, 0 and j is 0, 1. Well, we can multiply that out because we know how to multiply a scalar times a vector. This is just the vector negative 3, 0, and this is just the vector 3 times 0 is 0, 3 times 1 is 3. And we can add vectors. We just add the first components, negative 3 plus 0, negative 3. And we have 0 plus 3, that is 3. All right? And we can see that this form here written in standard unit vectors is the same as the component form. And you can just see, hey, obviously these are just the coordinates of the terminal points in standard position. Negative 3 is the first coordinate, 3 is the second coordinate, so it breaks up into i's and j's. All right? The usefulness is that this can be used with algebra or as an algebraic expression, where this it has to be worked with a little differently. So as we just saw in that last example, if a vector is not in standard position, well, we can still describe it, okay, in component form. So here let's have the component form and the magnitude of this vector v, which is from C to D. All right. So we're going to do very similar to what we just did. V is, we're going to subtracting the x coordinates. We have this point here is 5, 5, 3. This point here is 1, 5. So let's subtract the x coordinates, 5 minus 1, and then the y coordinates, 3 minus 5. And this will give us 4 and negative 2. As we can see, we are going right 4, down 2. So that would be the standard form of this vector, the equivalent vector in standard position. All right, so there we have v in component form. We weren't asked to write this in ij form, but I'm going to go ahead and do it just as an example. This would be 4i minus 2j. That's all there is. And the magnitude, to find the magnitude, that's the absolute value of our vector. That's how we write it. And it's the square root of 4 squared plus negative 2 squared. And that's going to be the square root of 16 plus 4, which is 20, which is going to be simplified to 2 square root 5. So there's our magnitude. All right. Finally, we're going to want to work with some directions. And here's where our trigonometry comes in. So here we have a vector v, and it's at some angle with the x-axis. And we want to define it using that information. So if we have horizontal and vertical components of v, let's find those in terms of theta. So let's call this, well, let's use x. And let's call this y. All right? So in terms of theta and v, we need an equation for x. Well, we know this. Now, first of all, this length of this line, we have a name for it. It's the absolute value of v, which is the magnitude of v. And we know the cosine of v, the cosine of theta is x over the magnitude of v. We also know the sine of theta is y over the magnitude of v. Okay? And so we can solve this for x and y, multiply both sides by magnitude of v. Magnitude of v times the cosine of theta is x. Magnitude of v times the sine of theta equals y. Okay? And the x and y coordinates just give us our 2 points, our 2 coordinates, that is. So that is the x coordinates, and this is the y coordinate. So written in terms of standard unit vectors, we have that. Okay? And finally, if we say that we want to find a unit vector, well, the unit vector is just going to take our vector v and divide it by the magnitude. Well, if we divide this whole thing by the magnitude, those are just going to go away. Okay? And so that just gives us the unit vector. Unit vector is v divided by the magnitude of v. Well, when we divide all of that by the magnitude, we're just going to get cosine of theta times I plus the sine of theta times j. And that's how we find the unit vector, if you know the angle that the vector is at. Finally, if we want to find the magnitude and the angle of a vector, because we see that that is really useful to know those things, if we know the vector's terminal point, well, we know how to find the magnitude here. The magnitude of our vector, call it v, is going to be the square root of 3 squared plus 2 squared, which is 9 plus 4, which is 13. And then the directional angle, well, if this is 3 and this is 2, and we're just going to find tangent. We know theta is the inverse tangent, of 2/3. And that's approximately 33.7 degrees. So there you have it. So we can find the angle if we know the terminal point. And if we know the angle and we know the magnitude, well, that really quickly helps us, or gives us a way to find the vector here using the cosine and the sine. There you have it. So have fun with your vectors.